Did you know that a single teaspoon of a white dwarf would weigh as much as an elephant here on Earth? These incredible objects are the final, glowing embers of stars, much like our own sun. They are the universe's ultimate retirement plan for about 97% of all stars. A white dwarf is what's left over when a star has exhausted its nuclear fuel, shed its outer layers, and settled down for a long, quiet cool-down period that can last for trillions of years. It's a stellar core, exposed to the cosmos, fantastically dense and still blazing with leftover heat from a lifetime of fusion. They are not making new energy, but they are far from being inert, boring rocks in space. When you look up at the night sky, you are seeing stars in various stages of their lives. Some are stellar nurseries, just beginning to ignite. Others are in their stable, middle-aged phase, like our sun. And some are nearing the end, swelling into red giants. The white dwarf is the next chapter in that story for most of them, the final, compact, and surprisingly beautiful stage. Imagine our sun, a million-mile-wide ball of incandescent gas, shrinking to an object no bigger than Earth. A cosmic transformation, grand to small, yet so powerful in its density. These stellar remnants are common, ghosts of stars past, a window into our solar system's future. The journey to becoming a white dwarf begins when a low to medium mass star like our sun starts to run out of its primary fuel, hydrogen. For billions of years, fusion pushes out while gravity pulls in. As the core hydrogen is depleted, the balance breaks. Gravity wins, compressing the core and spiking its temperature. A shell of hydrogen ignites around an inert helium core. The outer layers puff up. The star swells into a red giant, enormous, luminous, relatively cool, and hundreds of times its original size. The expanded atmosphere becomes tenuous, held only weakly by gravity. Powerful stellar winds blow these layers away, forming a beautiful, expanding cloud of gas and dust. A planetary nebula. Not a planet, just the star shedding its skin. Left behind at its heart is the star's hot, dense core, a newborn white dwarf, searingly hot, surface temperatures exceeding 100,000 degrees C, bathing space in intense ultraviolet light. Once born, the white dwarf reaches a new equilibrium. No more fusion. So what stops gravity from crushing it? The answer, quantum mechanics. Electrons are packed so tightly they enter electron degeneracy, like a cosmic parking garage with every spot filled. They resist further squeezing, creating pressure that holds the star up. Most white dwarfs are carbon-oxygen cores, layered by gravity, with a thin skin of hydrogen or helium. The most mind-boggling trait of a white dwarf is its density. A typical white dwarf can have a mass like our sun, but be squeezed into a sphere roughly Earth-sized. That's about 1,000,000 times denser than water. A sugar cube of white dwarf matter would weigh several tons. Electrons are stripped from nuclei, forming a degenerate electron gas that supports the star. The gravity is extreme. Surface gravity about 100,000 times Earth's. Stand there and you'd be crushed into a paste of atoms. Gravity sorts material. Heavy elements sink. Light elements float, forming a thin hydrogen or helium atmosphere just meters deep. That's why we often only see spectral lines of light elements. But electron degeneracy pressure isn't infinite. Subrahmanyan Chandrasekhar calculated a limit in the 1930s, about 1.4 times the sun's mass, the Chandrasekhar limit. Beyond it, gravity overwhelms electron pressure, and the star collapses catastrophically, triggering a runaway thermonuclear explosion, a Type Ia supernova. That limit divides stellar fates. Cores below it cool as white dwarfs. Above it, they explode. Because Type Ia supernovae have consistent peak brightness, they're standard candles for measuring cosmic distances. Many white dwarfs drift alone, but a great number live in binaries, locked in a gravitational dance. Close pairs get exciting. The white dwarf can pull gas from its companion. Hydrogen-rich gas doesn't fall straight in. It spirals into a hot accretion disk, glowing in X-rays. Gas piles on the surface, pressure and temperature build. And a runaway thermonuclear flash erupts. A nova, making the star brighten dramatically over days. Unlike a supernova, a nova only blows off the surface layer. The white dwarf survives and repeats. Famous example, Sirius. The brightest star in our sky is a binary, Sirius A and its faint white dwarf companion, Sirius B. Its existence was predicted from Sirius A's wobble before it was seen. Sirius B packs nearly the Sun's mass into roughly Earth's size, showing the fate of Sun-like stars. If accretion pushes a white dwarf over the Chandrasekhar limit, a type Ia supernova obliterates it, briefly outshining its host galaxy. Because they explode at a specific mass, their brightness is consistent, vital for mapping the expanding universe. In pairs, white dwarfs can be quiet thieves, or cosmic detonators. Single photorealistic Earth-sized white dwarf drifting in starfield. Contemplative wide shot. Why care about tiny, dense, fading stars? White dwarfs are more than relics. They're cosmic laboratories and historical records. They let us test physics under densities and pressures impossible on Earth. Proof of quantum rules holding up an entire star. Their slow cooling makes them cosmic clocks. The coolest white dwarfs in a cluster reveal its age. Through novae, and especially type Ia supernovae, white dwarfs create and disperse heavy elements, iron, nickel, silicon, that seed new stars and planets. The iron in your blood, the calcium in your bones, flung across the galaxy by stellar explosions. Let's correct a myth. Calling them dead stars isn't quite right. A white dwarf persists, glowing for trillions of years. It's more like a star in retirement. The fusion factory has shut down, but the remnant remains, a monument to the star that was. White dwarfs embody transformation, extreme physics, and the enduring legacy stars leave behind.